As you rest peacefully tonight, beneath the familiar warmth of a world bathed in sunlight for billions of years, imagine the unimaginable. What would happen if the sun suddenly ceased to exist? Not dimmed, not cooled, but instantly vanished, disappeared from space as if it had never been there at all. This scenario violates everything we know about physics and could never actually happen. Yet, exploring this thought experiment reveals profound truths about how dependent Earth is on our star, how quickly catastrophe would unfold, and how the physics of light, gravity, heat, and orbital mechanics govern every aspect of our existence. Tonight, as you drift toward sleep, you'll journey through the timeline of disaster that would follow the sun's disappearance, discovering what would happen in the first seconds when light stops arriving, the first minutes when gravity's grip releases, the first hours as darkness falls and temperatures plummet, the first days as Earth's atmosphere begins to freeze, the first weeks as the last vestiges of warmth disappear, and the long, dark future of a frozen world drifting through interstellar space. Demonstrating through this impossible scenario just how perfectly our planet is positioned within the sun's life-giving influence. The sun, a medium-sized yellow star 93 million miles from Earth, contains 99.86% of all the mass in the solar system. Its nuclear fusion reactions, converting 600 million tons of hydrogen into helium every second, generate the light and heat that make Earth habitable, drive weather and ocean currents, power photosynthesis, and ultimately provide nearly all the energy that sustains life. Remove the sun, and you remove the foundation upon which our entire world is built. This thought experiment is entirely impossible in reality. Stars don't simply vanish, and even if all nuclear fusion in the sun's core stopped instantly, which it couldn't, the existing heat and light would continue radiating for millennia as the energy slowly works its way from the core to the surface. But imagining instantaneous disappearance allows us to explore the consequences with clarity, revealing the interconnected systems that depend on our star and the timescales on which various catastrophes would unfold. The scenario also violates Einstein's theory of relativity in interesting ways. Information, including gravitational information, cannot travel faster than light. If the sun somehow vanished, Earth wouldn't know about it instantly. The last light would take 8 minutes and 20 seconds to arrive, the time it takes light to travel from sun to Earth. And the change in gravitational field would propagate at the same speed. For those final 8 minutes and 20 seconds, Earth would continue orbiting a sun that no longer exists, held in gravitational thrall by information traveling through space at light speed. Understanding what would happen if the sun disappeared requires understanding multiple interconnected systems, the physics of light propagation, orbital mechanics, thermodynamics, atmospheric science, geophysics, and biology. Each system would fail on its own timescale, creating a cascade of consequences that would transform Earth from a vibrant, living world into a frozen, dark, lifeless sphere drifting through the void, perhaps eventually to be captured by another star's gravity billions of years in the future, or perhaps to wander alone through interstellar space for eternity. The thought experiment is humbling, revealing how fragile Earth's habitability is, how dependent we are on the sun's continued existence, and how precisely balanced the conditions must be to support life. We live within a narrow, habitable zone, the Goldilocks region around the sun where temperatures allow liquid water, and Earth's position within that zone, combined with our atmosphere's greenhouse effect, creates the stable climate that has allowed life to evolve and flourish for billions of years. As you prepare to explore this impossible scenario tonight, rest in the comforting knowledge that the sun will continue shining for another 5 billion years, that the catastrophes you're about to imagine will never occur, and that you can safely contemplate the end of everything while remaining secure in the warmth and light that will greet you tomorrow morning when you wake. Demonstrating that thought experiments allow us to explore scenarios we hope never to experience, while gaining deeper appreciation for the cosmic circumstances that make our existence possible. The first 8 minutes, light's final journey. Journey now through the first 8 minutes and 20 seconds after the sun's impossible disappearance, discovering what would happen during those final moments when the last sunlight crosses the 93 million miles between sun and Earth, when the world continues its normal routine in ignorance of the catastrophe that has already occurred, and when the day transitions to an endless night unlike any humanity has ever experienced. At the moment the sun vanishes, nothing on Earth changes immediately. The sunlight illuminating the daytime side of the planet was emitted 8 minutes and 20 seconds earlier and is still traveling through space at 186,000 miles per second. People continue their activities, unaware that the source of the light they're seeing no longer exists. The sky remains blue. Plants continue photosynthesizing. Solar panels continue generating electricity. And everything appears normal during these final minutes of sunlight. For someone on the nighttime side of Earth at the moment of disappearance, the darkness would seem no different than any other night, until the moment the sun should rise. As Earth's rotation brings dawn locations toward where the sunrise should occur, the sky remains dark. No twilight brightens the eastern horizon. No golden glow announces the approaching day. No sun crests the horizon. Instead, darkness simply continues, and the realization would gradually dawn, ironically, that something is terribly wrong. Exactly 8 minutes and 20 seconds after the sun's disappearance, the last photons of sunlight arrive at Earth. At this moment, several things happen nearly simultaneously. The sky goes instantly dark, not the gradual dimming of sunset, but immediate blackness as the final sunlight passes and no more follows. The daytime sky, previously blue from scattered sunlight, turns black, revealing stars that are normally invisible during the day. The temperature stops rising and begins its inexorable fall. The psychological impact of this sudden darkness would be profound and immediate. Humans who witnessed the instant transition from daylight to darkness would experience confusion, fear, and disbelief. The impossibility of the event, the sun doesn't just disappear, would create cognitive dissonance as people struggled to comprehend what they're experiencing. Emergency services would be overwhelmed with calls. Power grids would strain as everyone turned on lights simultaneously, and panic would begin spreading as the reality of the situation became undeniable. Photography and videography from these final minutes would capture the last images of sunlit Earth, pictures and videos that would become the final visual record of our world as it was before the catastrophe. These images would show people going about normal activities, unaware that they're experiencing the last sunlight Earth will ever receive, creating a poignant documentation of normalcy before the sudden transition to crisis. The immediate darkness would create traffic hazards as drivers accustomed to daylight suddenly find themselves in blackness, Street lights and building lights would provide some illumination, but the abrupt transition would cause accidents as eyes struggle to adapt and drivers react in confusion. Aviation would face similar challenges, with aircraft in flight suddenly plunged into darkness, though most modern aircraft systems would continue functioning, using instruments rather than visual references. Plants would immediately stop photosynthesizing as the light they depend on ceases. The chemical reactions that convert carbon dioxide and water into sugars using light energy would halt mid-process. Though plants wouldn't immediately die, they would simply shift to using stored energy reserves, able to survive in darkness for days or weeks depending on species and existing energy stores. The immediate effect would be minimal, but this moment marks the beginning of the end for nearly all plant life on Earth. Solar power generation would cease instantly, as photovoltaic panels stop receiving the light they convert to electricity. Solar farms providing electricity to millions of homes and businesses would go offline, creating power demands that other generation sources would need to meet immediately. The loss of solar power represents only a portion of global electricity generation, so power grids wouldn't collapse immediately. But the sudden loss would create challenges for grid operators. Temperature changes would begin immediately, but slowly. The atmosphere, land, and oceans contain enormous amounts of stored heat that would begin radiating into space. But this cooling process takes time. Surface temperatures might drop by only a few degrees in the first hour, as the greenhouse effect temporarily prevents rapid heat loss. The thermal inertia of Earth's systems means that while the temperature trend begins immediately, the catastrophic cold comes later. The psychological transition from day to eternal night would mark a profound moment in human history, the last time any human would see sunlight, the last time photosynthesis would occur in natural illumination, the last time solar warmth would touch the surface. These final 8 minutes represent the end of the world as we know it, though it would take time for the full consequences to unfold. As you rest peacefully tonight, imagine those impossible final minutes. Children playing in sunlight that left the sun before they were born, arriving only now to illuminate a world whose source has vanished. Office workers looking out windows at a blue sky sustained by photons, completing their final journey. And the sudden, shocking transition to darkness that would mark the beginning of Earth's transformation from living planet to frozen relic, demonstrating how dependent every aspect of our existence is on that continuous stream of light crossing space, every moment of every day. The first hour, when gravity lets go. Discover now what happens when gravity's information arrives, 8 minutes and 20 seconds after the sun's disappearance. When the change in gravitational field reaches Earth traveling at light speed. When our planet suddenly finds itself no longer bound in solar orbit. And when we begin moving in a straight line through space at 67,000 miles per hour, departing the solar system and embarking on a journey into interstellar space. According to Einstein's general relativity, changes in gravitational fields propagate at the speed of light, the same speed at which light travels. This means that when the sun disappears, Earth continues following its orbital path around where the sun used to be, until the gravitational information about the sun's absence reaches us. For 8 minutes and 20 seconds, We orbit nothing, held in place by gravitational influences that no longer have a source, following field lines that are about to update to reflect the new reality of a sunless solar system. The moment gravitational information arrives, Earth stops following a curved orbital path and begins moving in a straight line according to Newton's first law. An object in motion continues in motion in a straight line unless acted upon by an external force. With the sun's gravity suddenly absent, no force pulls us into a curved path, and we simply continue in whatever direction we were moving at the moment gravity ceased, what physicists call following a geodesic through space-time that's no longer curved by the sun's mass. Earth's orbital velocity is approximately 67,000 miles per hour, 30 kilometers per second. This becomes our escape velocity, the speed at which we drift away from where the sun used to be, heading out into interstellar space. The direction we travel depends on where Earth happened to be in its orbit when the sun vanished. If disappearance occurred when Earth was moving perpendicular to the line between Earth and where the sun was, we'd head roughly tangent to our former orbit. If at other orbital positions, we'd travel in different directions, but in all cases, we're leaving the solar system forever. The other planets would similarly find themselves no longer bound in solar orbit, each departing in the direction it was moving at the moment gravity ceased. Mercury, moving faster at 105,000 miles per hour in its inner orbit, would shoot outward faster than Earth. Neptune, moving slower at 12,000 miles per hour in the outer solar system, would drift more slowly. Each planet would become a rogue world, destined to wander interstellar space until perhaps captured by another star's gravity billions of years in the future, or wandering alone forever. The Moon would remain gravitationally bound to Earth because its primary gravitational relationship is with Earth rather than the Sun. The Moon orbits Earth at about 2,300 miles per hour, and this velocity is far below the escape velocity from Earth's gravity, about 25,000 miles per hour. With the Sun gone, Earth and Moon would continue orbiting each other as a binary system, drifting through space together, maintaining their monthly cycle of lunar phases, though the phases would be illuminated only by starlight and perhaps the faint glow of city lights from Earth. The loss of solar gravity would affect more than just planetary orbits. Asteroids, comets, and all the countless smaller objects in the solar system would similarly find themselves freed from the sun's gravitational dominance. The asteroid belt between Mars and Jupiter would disperse, each asteroid traveling in its own direction. Comets in the Oort cloud, the distant spherical shell of icy bodies surrounding the solar system, would gradually drift away, no longer loosely bound to the sun's distant gravitational influence. Interestingly, the sudden transition from curved orbital motion to straight-line motion would be imperceptible to humans on Earth's surface. We don't feel orbital motion any more than we feel Earth's rotation. Both are constant velocities that create no sensation of acceleration. The switch from circular to linear motion would involve no jerk, no sudden change in felt gravity, no indication that anything had changed except for observations of where we are relative to the stars, which would show that our path through space has transformed from a closed ellipse to an open straight line. Within an hour of the gravitational change, Earth would have traveled approximately 67,000 miles from where it was when gravity ceased, roughly the distance to the Moon, but in a straight line away from the former solar system rather than in orbit. we'd be embarking on what would eventually be a journey of truly astronomical distances, traveling away from the sun's former location at a speed that would carry us about 600 million miles per year, roughly the distance from Earth to Jupiter. The change in Earth's trajectory would alter our long-term cosmic environment, but wouldn't immediately affect conditions on the surface. The gravitational forces we feel, Earth's own gravity pulling us toward the planet's center, the moon's tidal forces, the centrifugal effect from Earth's rotation, would all remain unchanged. Life on the surface would be affected by darkness and cooling, not by the change from orbital to linear motion through space. Over years and centuries, Earth's new trajectory would carry us farther and farther from the sun's former location and from the other planets, gradually increasing the distance between us and any other solar system objects, until we're truly alone in the vast emptiness of interstellar space. A rogue planet, dark and frozen, carrying the remnants of what was once a living biosphere, traveling through the galaxy as an isolated world that might not encounter another stellar system for billions of years, or might pass close to other stars and potentially be captured into new orbits, beginning a new chapter as a planet of a different sun. As you drift towards sleep tonight, imagine Earth suddenly released from 4.5 billion years of solar orbit, beginning its long, lonely journey through interstellar space, traveling at 67,000 miles per hour in a straight line toward no particular destination, carrying with it the moon as companion and the memory of the sun that once gave it light, warmth, and life, demonstrating through this impossible scenario that orbital motion is not a stable equilibrium, but a constant falling toward a central mass. And without that mass, there is nothing to fall toward, and motion simply continues in whatever direction it was already going. The first week, the big freeze begins. Journey now through the first week after the sun's disappearance, when the catastrophic cooling of Earth accelerates, when temperatures plummet toward values never experienced in human history, when the atmosphere begins to condense and eventually freeze, and when the biological consequences of darkness and cold transform Earth from a living world into a frozen, sterile environment hostile to nearly all forms of life. Within the first day after darkness falls, average global temperatures would drop by approximately 20 to 30 degrees Fahrenheit as Earth's surface radiates heat into space faster than it can be replenished. The rate of cooling would vary by location. Desert regions with dry air would cool faster than humid coastal areas because water vapor in the atmosphere acts as a greenhouse gas that slows heat loss. Cloud cover would initially slow cooling by trapping infrared radiation, but as temperatures drop, cloud physics would change in ways that eventually accelerate cooling. By the end of the first week, average global temperatures would have fallen to around -100 degrees Fahrenheit, far colder than the coldest temperatures ever naturally recorded on Earth, about -128 degrees Fahrenheit at Vostok Station in Antarctica. But unlike Antarctic cold, which results from months of winter darkness in a region already ice-covered, this global cold would affect every latitude and all ocean areas simultaneously. Tropical regions that have never experienced freezing would find themselves in deep freeze conditions that would kill nearly all plant and animal life within days. The oceans, which contain enormous amounts of stored heat and cover 71% of Earth's surface, would initially moderate the cooling rate. Water's high heat capacity means it takes a lot of energy loss to change water temperature significantly. The upper layers of the ocean would begin freezing within the first week, starting at high latitudes and gradually expanding toward the equator. But deep ocean water would remain liquid for years, insulated by growing layers of surface ice that would eventually become hundreds of feet thick. As surface water freezes, it would release latent heat, the energy required to change state from liquid to solid, which would temporarily slow cooling. However, this effect would diminish as ice sheets thicken and insulate the remaining liquid water below, eventually allowing deeper layers to freeze as well. The complete freezing of the oceans would take decades or even centuries, but the process would begin immediately as surface temperatures plummet below the freezing point of seawater, about 28 degrees Fahrenheit due to salt content. The atmosphere itself would begin condensing as temperatures drop below the liquefaction points of various atmospheric gases. Nitrogen, which makes up 78% of the atmosphere, liquefies at negative 320 degrees Fahrenheit at sea level pressure. Oxygen, 21% of the atmosphere, liquefies at negative 297 degrees Fahrenheit. These temperatures are still far below what would be reached in the first week, but the trajectory toward atmospheric collapse would be established, with some gases beginning to condense in high-altitude regions where temperatures are already coldest. Water vapor, already a minor component of the atmosphere at about 1 to 4%, depending on temperature and humidity, would freeze out within the first week, as temperatures drop below water's freezing point. This would create worldwide snowfall as atmospheric moisture condenses, then freezes, and falls as snow that would accumulate on the frozen surface. The removal of water vapor from the atmosphere would eliminate a major greenhouse gas, accelerating cooling by reducing the atmosphere's ability to trap infrared radiation. Carbon dioxide, currently about 0.04% of the atmosphere, would begin condensing at negative 109 degrees Fahrenheit at sea level pressure, a temperature that would be reached within the first week in many locations. Dry ice, solid carbon dioxide, would begin forming in the atmosphere and falling to the surface, creating a landscape increasingly covered not just with water, ice, and snow, but with frozen carbon dioxide, giving parts of Earth an appearance similar to Mars's polar ice caps, which consist of both water ice and dry ice. Plant life would die en masse during this first week, without light for photosynthesis and with temperatures dropping far below freezing. Most plants would perish within days. Trees, shrubs, grasses, crops, all would freeze solid, their cellular structures destroyed by ice crystal formation that ruptures cell walls. The death of photosynthetic organisms would mark the elimination of the base of nearly all food webs, though the immediate starvation of herbivores and subsequent predators would take longer to unfold. Most animals would die within the first week from cold exposure, starvation, or the collapse of ecosystems they depend on. Humans would survive longer than most species due to our technology. Buildings can be heated using non-solar energy sources like fossil fuels, nuclear power, and geothermal energy. But the cascading failures of infrastructure, agricultural systems, and supply chains would create life-threatening challenges within days. Only locations with access to non-solar energy sources and stored food supplies would remain habitable, even temporarily. Underground ecosystems that don't depend directly on sunlight might survive somewhat longer. Deep-sea hydrothermal vent communities that derive energy from chemosynthesis rather than photosynthesis could potentially survive for years or even decades, insulated by deep ocean water that would take time to freeze. Cave-dwelling organisms, deep soil bacteria, and organisms living near geothermal features might persist in isolated pockets where Earth's internal heat provides energy, though they would face eventual extinction as their environments gradually cool or as food chains connected to the surface collapse. The transformation of Earth during this first week would be almost incomprehensibly rapid. From a vibrant, living world with liquid oceans, flowing rivers, active weather systems, and billions of organisms photosynthesizing, growing, and reproducing, to a frozen, sterile environment covered in ice and snow, with temperatures rivaling the coldest regions of the outer solar system, with nearly all life dead or dying, and with survivors limited to deep underground or deep ocean locations, temporarily insulated from the surface catastrophe. As you rest peacefully tonight in the warmth that will greet you tomorrow, imagine Earth just 1 week after the sun's impossible disappearance. Silent, dark, frozen, with ice sheets expanding across once temperate lands, with frozen forests standing as monuments to the life that was, with abandoned cities dark except for the few powered by remaining energy sources, and with the precious few survivors clustered around geothermal vents, nuclear reactors, or anywhere heat could be generated from non-solar sources, demonstrating through this impossible scenario just how narrow the temperature range is within which life can exist, and how dependent the entire biosphere is on the constant stream of solar energy that has sustained it for billions of years. The first year, atmospheric collapse. Contemplate now what happens during the first year after the sun's disappearance, when temperatures continue falling toward absolute zero, when Earth's atmosphere begins to collapse as gases liquefy and freeze, when the oceans complete their transformation into solid ice, kilometers thick, and when Earth becomes a world more similar to Pluto or Triton than to the vibrant planet it once was. By the end of the first month, average global temperatures would have reached approximately -200 degrees Fahrenheit, cold enough that carbon dioxide, one of the major greenhouse gases, would have almost entirely condensed out of the atmosphere and frozen onto the surface. The removal of CO2 would eliminate another mechanism for retaining heat, further accelerating cooling. Dry ice deposits would accumulate wherever CO2 had condensed, creating landscapes covered with both water ice and frozen carbon dioxide. Within 3 months, temperatures would approach -300 degrees Fahrenheit, reaching the liquefaction point of oxygen. At these temperatures, oxygen would begin condensing from the atmosphere, initially forming liquid droplets that would fall like rain, then freezing as solid oxygen upon contact with the already frozen surface. The atmospheric pressure would begin noticeably declining as oxygen is removed from the gas phase, making breathing impossible, even if temperatures were somehow survivable. By 6 months, nitrogen, the most abundant atmospheric gas, would begin condensing as temperatures reached approximately -320 degrees Fahrenheit. Liquid nitrogen would rain from the sky, then immediately freeze on contact with the surface, creating deposits of frozen nitrogen accumulating everywhere. The atmospheric pressure would drop dramatically as the major component of the atmosphere condenses, eventually leaving only trace gases in vapor phase, as Earth's atmosphere effectively collapses into a thin shell of frozen gases on the planet's surface. Within a year, temperatures would stabilize at around -400 degrees Fahrenheit, just 60 degrees above absolute zero, negative 460 degrees Fahrenheit, the theoretical lower limit of temperature where molecular motion nearly ceases. At these temperatures, all atmospheric gases except perhaps traces of helium and hydrogen would be frozen solid on the surface. The atmosphere would consist of a thin layer of perhaps just 1% of its original pressure, with most gases existing as solid deposits on the ground rather than in vapor phase overhead. The oceans would be completely frozen to enormous depths. While surface waters would freeze within weeks, the complete solidification of the ocean would take longer because water is a poor conductor of heat, and thick ice sheets insulate remaining liquid water below. However, within a year, ice sheets kilometers thick would cover all oceans, with any remaining liquid water restricted to the very deepest ocean trenches, or near hydrothermal vents where Earth's internal heat temporarily prevents complete freezing. The loss of the liquid ocean would eliminate the majority of Earth's heat storage capacity. The ocean currently acts as a vast thermal reservoir that moderates climate, storing heat during summer and releasing it during winter, distributing heat from equator to poles through currents, and generally preventing rapid temperature changes. With the ocean frozen solid, Earth loses this thermal buffer and becomes more responsive to whatever heat sources remain, primarily Earth's own internal geothermal heat. Geothermal heat from Earth's interior would become the planet's only significant heat source. Currently, geothermal heat flow averages about 0.1 watts per square meter, absolutely trivial compared to the roughly 1,000 watts per square meter that sunlight provides to Earth's daytime surface. However, with no sunlight, geothermal heat becomes the only energy keeping Earth's interior from eventually cooling to match the surface temperature, though this equilibration would take billions of years due to the insulating effects of rock. Volcanic activity would continue for a time, powered by radioactive decay of elements like uranium, thorium, and potassium in Earth's mantle, and by residual heat from Earth's formation. Volcanoes would release heat, gases, and molten rock onto the frozen surface, creating temporary warm spots where ice might melt back to liquid water, potentially providing brief refuges for any extremophile organisms that had survived the initial freeze. However, these volcanic oases would be short-lived, quickly refreezing when volcanic activity ceased. Hydrothermal vents on the ocean floor, currently supporting unique ecosystems independent of sunlight through chemosynthesis, would continue operating for some time, powered by Earth's internal heat. These communities of bacteria, tube worms, clams, and other organisms might survive as perhaps the last bastions of active life on Earth, living beneath miles of frozen ocean in eternal darkness, sustained by chemicals released from seafloor vents. These ecosystems could potentially survive for thousands or even millions of years before cooling or chemical exhaustion ends them. Radioactive decay of elements throughout Earth's crust and mantle would continue producing heat at current rates for millions of years, very gradually declining as radioactive isotopes decay away. This decay heat, while insufficient to prevent surface freezing, would maintain temperature gradients within Earth's interior, keeping the outer core liquid, important for maintaining Earth's magnetic field, the mantle solid but slowly convecting, and the inner core solid. Earth's internal structure would remain largely unchanged despite surface catastrophe. Tidal heating from the moon's gravity would continue, though at reduced levels, as Earth's rotation gradually slows due to tidal friction. The Moon would continue orbiting Earth, creating small tidal bulges in the frozen surface, and whatever residual liquid exists in deep ocean trenches. This tidal flexing would generate small amounts of heat through friction, adding slightly to Earth's meager heat budget, though far too little to significantly affect surface conditions. The transformation of Earth within the first year from a planet with liquid ocean, flowing atmosphere, active weather, and abundant life to a frozen, nearly airless world, covered in ices of various compositions, with temperatures barely above absolute zero, and with only traces of life potentially surviving in the deepest, most isolated environments, would represent one of the most dramatic planetary changes imaginable, accomplished in the span of just 12 months after the Sun's disappearance. As you drift towards sleep tonight, secure in the knowledge that the Sun will rise tomorrow, and for billions of years to come, imagine Earth 1 year after its impossible catastrophe, a world transformed beyond recognition, with kilometer-thick ice replacing the oceans, with frozen atmosphere deposited on the surface, with temperatures so cold that matter behaves in ways rarely seen outside laboratory cryogenic experiments, and with the only remaining heat coming from Earth's own interior, insufficient to do more than prevent complete thermal death, but maintaining a faint pulse of geological activity that would continue for eons, demonstrating that while Earth's surface depends entirely on solar energy, the planet's interior contains enough stored heat to remain geologically active long after the surface has frozen into complete stillness. The long dark future, eternity in the void. Rest now in contemplation of Earth's long-term fate after the Sun's disappearance. The journey through interstellar space lasting millions or billions of years, the possibility of eventual capture by another star, the ultimate fate of a rogue planet wandering through the galaxy, and what this impossible thought experiment reveals about how precious and precarious our existence is, how perfectly positioned we are within the cosmos, and how much we depend on cosmic circumstances continuing as they have for billions of years. Earth would continue its journey through interstellar space at approximately 67,000 miles per hour, moving in a straight line away from the Sun's former location. This velocity, while fast by everyday standards, is almost inconsequential on galactic scales. The Milky Way galaxy is roughly 100,000 light-years in diameter, and at Earth's velocity, it would take about 18 million years to travel just 1 light-year, the distance light travels in 1 year. The nearest star to our former solar system, Proxima Centauri, is 4.2 light-years away. If Earth happened to be traveling directly toward it, which would be astronomically unlikely given the random direction of our orbital motion at the moment of the Sun's disappearance, it would take roughly 75 million years to reach it. More likely, Earth would pass nowhere near any particular star, drifting through the vast empty spaces between stars where matter is so sparse that individual atoms might be separated by inches or feet, rather than the microscopic distances typical of solids, liquids, and gases. The galaxy contains roughly 200 to 400 billion stars, spread throughout a disk roughly 100,000 light-years across, and about 1,000 light-years thick in the spiral arms where our Sun is located. The average distance between stars in our region of the galaxy is about 5 light-years. Given these enormous distances and the random direction of Earth's trajectory, the probability of passing close to another star is extraordinarily small. We might wander through the galaxy for billions of years without ever approaching another stellar system closer than light-years away. However, the galaxy itself is not static. Stars orbit the galactic center, creating a complex dance where stellar positions change over millions of years. The Sun's former orbit around the galactic center took approximately 230 million years to complete, and Earth, having inherited the Sun's galactic orbital motion in addition to its solar orbital motion, would continue moving through the galaxy in a path influenced by the combined mass of all galactic stars, dark matter, and the supermassive black hole at the galactic center. Over time, scales of hundreds of millions or billions of years, Earth might eventually pass close enough to another star to be captured by its gravity, becoming a planet of a new stellar system. If this captured Earth passed through the new star's habitable zone, and if sufficient time had passed for the star to warm the frozen surface, liquid water might return. Though whether life could re-emerge from frozen remnants or would need to start completely anew is unclear. More likely, Earth would be captured into an orbit outside the habitable zone, remaining frozen, but now circling a new sun. Alternatively, Earth might wander through the galaxy for billions of years without ever being captured, remaining a rogue planet indefinitely. Astronomers estimate that there might be billions of rogue planets in our galaxy alone, worlds ejected from their birth stellar systems or formed in isolation, drifting through interstellar space. Earth would join this population of wandering worlds, a testament to the catastrophe that befell our solar system, and a frozen time capsule preserving a record of the life that once flourished here. The geological activity that continues on Earth, powered by radioactive decay and residual heat from formation, would very gradually decline over hundreds of millions of years as radioactive elements decay and aren't replenished. Volcanic activity would slowly cease, plate tectonic motion would grind to a halt, and Earth's interior would cool toward equilibrium with the frozen surface. However, this process would take so long that Earth might be captured by another star or experience other cosmic events before becoming completely geologically dead. Earth's magnetic field, generated by convection currents in the liquid outer core, would continue for millions of years, as long as the core remains liquid and convective. However, as Earth's interior slowly cools without solar heating, the outer core would eventually solidify, ending the geodynamo that generates the magnetic field. Without this field, Earth would lose its protection from cosmic rays and solar wind, from whatever star it might be near. Though for a frozen, lifeless world, this would be irrelevant. The Moon would continue orbiting Earth throughout the journey through interstellar space, though the tidal interactions between Earth and Moon would continue very slowly, transferring Earth's rotational energy to the Moon's orbital energy. Eventually, after billions of years, Earth and Moon might become tidally locked to each other, with the same faces always pointed toward each other, orbiting their common center of mass in a stable configuration that would persist indefinitely, unless disrupted by gravitational interactions with other stellar systems. The frozen biosphere would remain indefinitely, preserved at the extremely low temperatures of interstellar space. Any organisms frozen into the ice, bacteria, plants, animals, humans, would remain frozen essentially forever, protected from decay by the complete absence of liquid water and the extremely low temperatures that prevent any chemical reactions from occurring. Earth would become a museum of its former life, a frozen archive that might someday be discovered by intelligent beings from another civilization and studied to understand the life that once thrived here. The ultimate fate of Earth in this scenario would depend on cosmic circumstances over billions of years. Whether it's captured by another star, whether it collides with other rogue planets or asteroids during its journey, whether it survives the eventual collision between the Milky Way and Andromeda galaxies, predicted to occur in about 4 billion years, and whether it exists long enough to witness the far future of the universe, when stars have exhausted their fuel and the cosmos enters its final phases of evolution. This thought experiment, while utterly impossible in reality, reveals profound truths about our existence. We live at the bottom of a gravity well, held in orbit by a star that provides the energy necessary for all life. We exist within a narrow temperature range between the frozen lifelessness of deep space and the sterilizing heat too close to our star. We depend on the stability of cosmic circumstances, the sun's steady burning, Earth's orbit remaining within the habitable zone, the atmosphere retaining just the right composition to create moderate greenhouse warming that have persisted for billions of years and enabled the evolution of complex life, including consciousness, that can contemplate these circumstances. As you drift into peaceful sleep tonight, rest in the comforting certainty that the sun will continue burning for 5 billion more years, that Earth will remain in its orbit for billions of years more, that tomorrow will bring another day of sunlight and warmth, and that the catastrophic scenario you've imagined will never occur. Yet, carry with you an appreciation for how precious and improbable our existence is, how dependent we are on cosmic circumstances we did not create and cannot control, and how the thin layer of atmosphere, the narrow temperature range, and the continuous stream of solar energy create the conditions that make Earth not just a planet, but a living world, where conscious beings can wonder about the cosmos, explore impossible scenarios through thought experiments, and appreciate through understanding how remarkably perfect our position in the universe truly is. Sleep well, knowing you are safe, knowing the sun shines overhead or will rise again soon, knowing that life continues its eternal dance, powered by the star that has illuminated our days for 4.6 billion years, and will continue for billions more. And knowing that the thought experiment of the sun's disappearance serves not to frighten, but to illuminate, revealing through imagining loss what we possess, demonstrating through contemplating catastrophe how perfectly balanced our world is, and showing through exploring impossibility just how dependent every breath, every plant, every ecosystem, and every moment of warmth is on that vast nuclear furnace 93 million miles away, that transforms hydrogen into helium, and in doing so, makes possible everything we know as life, consciousness, and home. Sweet dreams beneath the stars, where Earth orbits safely within the sun's gravitational embrace, where solar energy streams continuously toward our planet at the speed of light, where the greenhouse effect maintains temperatures within the narrow range that allows liquid water, where photosynthesis converts sunlight into the chemical energy that flows through every food web, and where the impossible scenario of the sun's disappearance remains forever in the realm of thought experiments, useful for understanding, powerful for revealing dependencies, humbling in demonstrating our cosmic fragility, but comfortingly impossible, reminding you as you drift into sleep that the universe operates by laws that don't allow stars to simply vanish, that the sun's nuclear fusion will continue reliably for eons to come, and that you can rest peacefully, knowing that tomorrow will bring another sunrise, another day of warmth and light, another rotation through the cycle of day and night that has defined life on Earth since the first organisms learned to harvest solar energy billions of years ago.